Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Design circular queue. Leetcode 641. In this problem, we have to design the implementation of a circular double-ended queue, or also called Deque in short. A Deque or a double-ended queue is a linear data structure that allows insertion and deletion of elements from both ends, that is rear and front. And using a circular Deque gives us the added advantage of wrapping around when the Deque is full. Then the problem is to design MyCircularDeque class with the following operations. MyCircularDeque is a constructor method initializing the Deque with a maximum size of k. InsertFront adds an element at the front of the queue and returns true if the operation is successful, otherwise false. InsertLast adds an element at the rear of the Deque, returns true if the operation is successful or false otherwise. deleteFront deletes the element from the front of the queue, returns true if the operation is successful or false otherwise. deleteLast deletes an item from the rear of the Deque, returns true if the operation is successful or false otherwise. getFront returns the element from the front, -1 if the Deque is empty. Similarly, getRear returns the last element from the Deque and returns -1 if the Deque is empty. Similarly, isEmpty returns true if the Deque is empty and false otherwise. Similarly, isFull is opposite of isEmpty, which returns true if the Deque is full and false otherwise. So then in example 1, we are given the input like this. So first we will create a circular queue of size 3. So this is rear and this is front. Then it says insert last one. So we try to insert one at the rear of the Deque, and because the Deque has a space, we insert one successfully and return true. Then it says insert last 2. So we try to insert 2 at the rear of the Deque, and because there is still space available, we insert 2 successfully and return true. And now our rear moves here. Now it says insert front with value 3. And since there is space, we will insert 3 successfully and return true. And now the Deque is full. Now it says insert 4 at front, but because our Deque is full, the insertion fails and hence we return false. Then it says getRear. What is the value at rear? It is 2. So we will return 2 here. Then is our Deque full? We will return true because our Deque is actually full. Then it says deleteLast. So we remove the element from the rear, in this case element 2, successfully. So we will return true. And now we will reduce our rear to pointing to 1 again. Then it says insert front with value 4. So we insert at front with value 4 and now our front moves here. Then it says getFront. And because our front pointer is pointing to 4, we will return 4 in this case. And now we are done with all the operations. So now let's jump into the solution space. Now what data structure we can use to solve this problem? As the Deque is a linear data structure, following data structures come to mind, that is array, singly linked list or doubly linked list. An array is a good fit for the circular queue because we can use indices at the front and rear to insert, access and delete elements in O of 1 time. Also, we can use modular arithmetic, that is use modulo operator to handle the circular nature of the Deque. So as soon as front or rear indices are out of bounds of the array, we can actually use modulo operator with the array length to get the index within the array bounds. But we are not accessing the elements in the middle of the Deque, just at the both ends. So the array insertion and deletion in O1 time are not helping much, at least in this area, but we only care about the rear and front indices. Also, when we use array, we cannot support dynamic sizing. And in this problem, our Deque actually has fixed sizing. So array shouldn't be a problem, and that's why array will be a useful data structure. But we cannot say the same thing for the singly linked list because it only has pointer to the next node, and because of this it is inefficient for the operations at the front of the Deque, where accessing the previous node will require traversing from start or head of the linked list, and that will result in time complexity of O of n. For example, if we have to delete the element at the front, first we have to traverse through all the elements from the start of the list, and then when we are at the previous node, we delete the element at the front of the linked list, and now the front of the Deque will be pointing to the previous element in the linked list. So because of this, we cannot use singly linked list. And finally, we come to doubly linked list. It is also a suitable data structure because now for each node, we will have pointers to both previous and next node. So we can actually again perform all of these operations of the Deque in O of one time. It also provides dynamic resizing and is flexible with the memory allocation as well. So doubly linked list is also very useful when it comes to implementing double-ended queue. But it also has its con. It involves pointer arithmetic, so we need to handle some edge cases when we are inserting and deleting the elements from the Deque. So now let's jump into the code part, looking at the array-based implementation first. First, let's define the array where we will store all the elements of the Deque. Also, we will need front pointer, rear pointer, and the size of the Deque. So in the constructor, we can initialize all of them. So initially, our Deque or array size will be equal to k. So we can initialize our array accordingly. Front will be pointing to k minus 1, that is the last point in the array initially. Rear will be pointing to 0, and our size will also be 0 because we have not inserted any element so far. So now that we have initialized, now let's first look at the insertFront function. So when we are inserting the element at the front or at the end, we have to check if Deque is full or not. Because if the Deque is full, then we can just return false in this case because we cannot insert the element anymore. And how will we know if the Deque is full or not? We can just check if size is equal to Deque length, because that means the array is totally full. Now, if we are here, that means the Deque is not full. So we can actually insert the element at the front, increment our size as well, and return true. But we also need to update the front value. And how will we do that? We will decrement front value by 1 and move front pointer to the left. For example, take the Deque of size 3 and we have inserted the first element, say 3, at the front. And now if we have to fill in the element again at the front, what will be the next position of the front? It will be stored at the second position. So that's why we have to do front minus minus. But given the circular nature of Circular Deque, this may not be enough. What if front is at the start of the array? So instead of filling the last index in the array, we fill in the 0th index. And now if we do front minus minus, then front will become -1, which will result in index out of bound. So to fix this, we will use modulo operator. Also in different programming languages, including Java, the modulo operation can yield a negative result when applied to a negative number. For example, -1 modulo 3 may result in -1 instead of 2, which will again give index out of bounds error. So to fix this, we will also add declength to the result, and we will set front as front -1 plus declength modulo declength. Then we will get -1 modulo 3 as -1 plus 3 modulo 3. So that will give us 2 modulo 3, that is 2 instead of -1. So now next time if we have to insert the element and the space is available, we will actually fill in the value at this point, right? So this is how the insertFront will work. Similarly, now we will fill in insertLast. We will check if Deque is full. If yes, then we will return false. Otherwise, we will set the value at the rear index. Now we have to do rear plus plus, but we will also fix this one as well. Increment the size by 1 as we added the value here, and return true because insertion was successful. But again, due to the circular nature of the Deque, we may have index out of bound in the fixed size array. So to avoid this, we will again use a modulo operator. So we will set rear as rear plus 1 modulo Deque length. I just realized that we should use the variable k as a capacity of the Deque instead of using the longer variable name Deque.length again and again. So that will save some time. Let's set this up in the constructor and use it instead of Deque.length. Okay, we can insert the element at the start. We can insert the element at the end. Now we have to do the same thing for delete as well. So if you have to delete the element from the front, we should check the opposite of is full. We should check if the Deque is empty. If the Deque is empty, then we cannot delete anything. Then we will again return false. And how will we check if the Deque is empty? By checking if size is 0. If it is 0, that means Deque is empty. Now that we have checked if our Deque is empty or not, now our next step is to delete it. So now this time we will move front to the right. So how will we do it? We will just do front plus 1 modulo k, reduce the size, also return true. Similarly, for delete last, we will check if it is empty, then we cannot delete anything. So we will return false. But if we can, we will shift rear to the left by subtracting by 1. But again, to keep it in bounds, we will set rear equal to rear minus 1 plus k modulo k. We will subtract the size and we will return true in this case. Finally, to get the value at the front, how will we do that? Remember, when we are updating the value at the front, we move the front accordingly for the next update. For example, when we inserted value at the front, we move front to the left for the next insertion. So to get the value, we should go to the right by just adding 1 to the front and apply modulo operator k to stay in the bounds. So if deque is not empty, so before that, let's check if our deque is empty, then we cannot get any value at all. So we will return just -1 in this case. Otherwise, we will just return the value in the deque at the front by getting the value at the index front plus 1 modulo k. Similarly, we will do the same thing for the rear as well. So we will check if it is empty, then we will just return -1. Otherwise, we will return the deque value at rear -1 plus k modulo k. And now I think we have implemented all the methods. So let's run this code. Cool. Let's submit this code. Awesome. In terms of time complexity, all the operations take O of 1 time, except the constructor one, because there we are creating an array of length k. And the reason for this is because and inserting and updating the elements in the array using indices, which takes O of 1 time. So the overall time complexity is O of 1. And in terms of space complexity, it will be O of k because we are using the array of size k to store all the deque values. Now let's implement the circular deque using doubly linked list. First, we will start with the double list node class that defines the structure of each node in our doubly linked list. Each node will have a pointers to the previous and next nodes along with the value. Then let's define the sentinel nodes for the head and tail to simplify the insertion and deletion operations. Now we will not need front and rear because we are taking care of it with the double list node, but we will still need size and k. Let's initialize our doubly linked list node head and tail pointer. The head sentinel node will be pointing to the beginning of the deque and the tail sentinel node will be pointing to the end of the deque. So let's initialize these nodes and use dummy pointer technique. That is, we will have these nodes with some dummy values and we will not use them in the solution, but our insertion and deletion becomes easier because of that. Please refer this video for more details on the dummy pointer technique. So initially size will stay 0. We don't need front and rear now. Now let's connect these two nodes. Head is the front node, right? So its previous will be pointing to tail and tail is a rear node. So tail's next will be pointing to head. And this dot k and size will stay the same. Now insertFront method adds an item in the front of the deque. If the deque is full, we should return false. So let's fix isFull method. Instead of using deque array.length, we can now check if size is equal to k. That means the deque is full. We don't need this logic as well. Of course, we have to increment the size now if we are here. So now we will again just do double list node. So we will create a new double list node and pass in the value. Now let's try to understand how we can insert this node at the front of the deque. Suppose this is the newly created node and this is our linked list with following head or front pointer. Let's first connect node to the linked list. So we will set node.next to head and node.previous to head.previous. And in terms of code, we have to do node.next is equal to head and node.previous is equal to head.previous. Once we have done, now we have to detach these nodes, right? We have to break these connections. We will just do head.previous. Let's first label these connections. Let this connection be connection number 2 and this one be 1. Let's first break connection number 2. So we will just set head.previous.next, now pointing to the node. And now let's break connection number 1. So we will just do head.previous is equal to node. So we will need just these 4 lines. And now let's write these lines in the code. So first let's connect node to the list and then list to the node. And finally we will return true. Similarly, we will do the same thing for the insertLast as well. If the deque is full, we will return false. Otherwise, we will create a new node with the value. Now, first we add this node to the list. So how will we do that? We will just say node.next is equal to tail.next and node.previous is equal to tail. Let's get rid of these array-based lines. Now let's break the connection between the tail pointer and its next node. and insert this newly created node between the tail pointer and its next pointer. So we will just do tail.next.previous is equal to node and tail.next is equal to node. Now let's implement deleteFront function. First we will check if the deque is empty. If it is, then we will return false. Otherwise we will remove the node from the doubly linked list. Suppose this is our list and we are deleting the element from the front. So our front is here. Let's call our node that has to be deleted as current. So how will we do that? So to delete this node, we have to get rid of its connections from the list. So we will just do current.previous.next is equal to head and head.previous is equal to current.previous. And what will be the value of current? It will be head.previous because it is just the previous node from the head pointer. So this is how we will get rid of all the connections. And then this node will be garbage collected automatically by Java garbage collector. So let's do this in code now. So we will just do head.previous.next is head itself and head.previous is equal to head.previous.previous. So we updated the next pointer of current node's previous node and previous pointer of the head pointer. We will do the same thing for deleteLast as well. So we will just do tail.next.next.previous as tail and tail.next is equal to tail.next.next. We reduce the size and return true again. Now to get the value at the front, remember that head pointer and tail pointer are both dummy nodes. So to get the value at the front, we have to go to the previous node for head pointer and get its value. So we will return head.previous.val. Similarly, for the rear value, we will return tail.next.val. And now I think we are done. Let's run this code again. Let's submit this code. Cool. In terms of time complexity, nothing changes. It will still be O of 1. Of course, the constructor's time complexity is now improved to O of 1 as well. And in terms of space complexity, it will be O of k because we are creating a list of size k plus 2 to store all the elements of the deque. I hope this video was useful to you. If it was, please like, share and subscribe. The code link is in the description below. Thanks for watching. See you next time.